In this video, we're going over more additions of alkenes, and we're looking here at a review problem. We've seen Markovnikov's addition before, and we know that when we have an alkene in the presence of an HX, we're going to have the pi bond here attack this proton, and then we're going to kick out bromine. Now, where we place that proton is where Markovnikov's rule comes in, and it's really just a rule and doesn't really explain why. But it says when you have HX addition alkenes, the hydrogen attaches to the carbon with the most hydrogen atoms. Our carbon on this double bond that had the most hydrogen atoms are here. So we're going to add our hydrogen right here. That gives us this secondary carbocation. Now in your head, you might be thinking, well, wait, what about the other way? Remember that if I were to add the hydrogen in the middle one, that would give me a primary carbocation. So the way I like to remember it is that you form the most stable carbocation. And we're going to see this happen again and again. All right, and the next step of this HX addition across an alkene is that now we have a nucleophile that can add to our carbocation. Now we know that if this carbon center here was chiral, we would have both R and S. Let's now look at a reaction that we have seen before as well, and we're going to learn a new reaction. We know that in the presence of an alcohol, if we have a non-nucleophilic strong acid, we can end up getting the alkene. And this is that E1 reaction that we learned about. Now, another reaction that can give something that looks kind of similar is if we start with an alkene, and if we were to use catalytic H2SO4, so we still have H2SO4 present, and we're going to have a lot of water present. Remember, in this first reaction, we actually end up kicking out water. What you can end up forming is an alcohol. Notice that these two are just opposites of each other. The top reaction here, we have this alcohol forming an alkene, and then in the bottom we have the alkene making the alcohol. If we look at the mechanism, we're going to see that it's exactly the same as the E1 in the red there, but it is completely opposite. So let's go ahead and walk through the mechanism. So if we have our alkene, we have H2SO4. We're going to have addition of this hydrogen. It's going to go here. It's going to give us the most stable carbocation. Now, we have this conjugate base floating around, but we know this is non-nucleophilic. That negative charge is shared within that compound, but we do have a lot of water. So we're going to have water come over, and it's going to attack this carbocation. All right, and then now we're going to deprotonate because we need to isolate a neutral species. So we're going to take the electrons from the oxygen, pick up a proton, and those electrons go to the oxygen. All right, and there we have it. That's our desired alcohol. Notice all of these steps are reversible. Now I want to think about this top reaction up here that we said was E1. This was one that we've learned before. So this top one is a review. If you notice here, if we start our arrows or start our eye over here, if we start with the alcohol, okay, which is our E1 reaction, you'll notice here that the first step goes from an alcohol to a protonated alcohol. Well, that's the first step for an E1 reaction. So the mechanism for the E1 reaction, why don't we just review it and let's just write that out. Mechanism for E1. So I'm going to start with my alcohol. I'm going to have H2SO4. It's going to protonate. I'm going to go ahead and speed up the video just in case you don't want to walk through this with me. All right, and here we have our desired alkene. Now, what I want us to look at here is how similar these reactions are. They are microscopically the reverse. So this is introducing a new topic that we haven't talked about, this microscopic reversibility. Essentially, all that's saying is that all of the forward steps here, going from alkene, making a carbocation, having this protonated alcohol, forming out an alcohol, is exactly opposite of our E1 mechanism. So if I start here at the alcohol, okay, so E1, I start with an alcohol. I have a protonated alcohol, okay. If I go down here, I have a protonated alcohol, okay. I have a carbocation. I don't know where that little blue thing went. I have a carbocation, and now I have a carbocation. And in the first step here, I have an alkene, and in the last step, I have an alkene. Now, the arrows are all opposite. This is why it's exactly the opposite. These reactions are considered to be microscopically reversible because each of the intermediates that we make are the same intermediates in this E1 mechanism. This is a topic that will come up later on in your organic chemistry career, and I want to bring it up now, in that many times we draw these mechanisms and they look very different, right? Because we're starting with an alkene or we're starting with an alcohol. But actually, it just depends on where you go. So the E1 reaction, if we were starting from the alkene going back, it would look the same as this hydration of an alkene as we're going forward. Notice here, you've learned all of the steps in order to do this mechanism. It looks really new because you haven't seen it, but there are all the same concepts. Let's highlight a couple more here. We also still have, for hydration of alkenes, we still follow Markovnikov addition. Okay, where the H goes to the less substituted carbon. And then our nucleophile goes to the most substituted. Alkenes can also isomerize. And what this means here is we're actually going to be making the most substituted alkene, which we know is more stable, okay? And so the way that we're going to do this is that in the presence of acid, we know that these alkenes can be protonated. So we have a very strong acid, and if we protonate this, what do we get? Well, we have a carbocation. This is now kind of looking like an E1 reaction, right? We have a carbocation. We have different protons that we could remove. So here's our beta carbons, right? Now, our beta carbons in red there would give this less substituted alkene. And we know from our E1 studies that actually we want to take from this blue beta carbon because this would give us a double bond that's more substituted. So this is really all alkene isomerization is it's making a more stable alkene through something we've kind of talked about before. This alkene isomerization is essentially partially an E1. All right, and there we have it. That is our alkene. This is really, like I said, this looks a lot like the E1 reaction, but you're going to make the most stable. Alkene here. And this is through a carbocation intermediate. And it uses the same mechanism, but it's different. It looks different, right? So the key takeaway here is that alkenes do react with acids. They do get protonated. The resulting carbocation can undergo either nucleophilic attack or it can undergo an E1 type mechanism. So let's also make a note here. This is kind of this E1 type mechanism. Now, we didn't have a leaving group leave. We simply protonated our alkene. But you see how they're very similar. This reaction is under thermodynamic control. Typically, you would heat this in order to get the most stable and most substituted alkene. Reactions that are in equilibrium are under thermodynamic control, and the most stable alkene is the major product. All right, let's now do a practice problem where we bring together some of these ideas. Here I've got ethanol in the presence of catalytic H2SO4. Now, so far in this video, we've only looked at water being added with H2SO4. So this looks like a new reaction, but we can walk through the steps that we already know. All right, so I have an alkene, and I know that it reacts with acid. So I'm going to just draw this out. One of the keys with organic chemistry is you sometimes don't know what the product will be until you start drawing the mechanism. This is going to give you clues about where to go. And it's all because you've built up your intuition by learning the fundamentals here. So we know that the hydrogen will add on the least substituted or the one that already has lots of hydrogens. That makes sense because here we have a tertiary carbocation. Now, we know that we have this non-nucleophilic acid, but we also have some ethanol present. Now, ethanol, remember ET, here we go. It's just this guy. So ethanol can react with this carbocation, and it will do just that. This looks really similar to what we did before with water. But instead of hydrogen here, we have an ethyl group, okay? And so now what we can do is we can remove that extra proton. So we're just going to take another equivalent of ethanol. And we're going to deprotonate it. All right, and so our product here looks like this. Now, we didn't form a chiral center on this compound here, but we would imagine that if this carbon, if it were chiral, you would have both R and S. Okay, you would have both R and S there. So this is one of the ways that you can kind of expand what you already know. We haven't looked at using an alcohol, okay, like in this reaction, but we've done water before. The mechanism is very similar, same reactivity here. The key here is that once you protonate your alkene, you're going to make the most stable carbocation. And this is that Markovnikov's rule of the hydrogen adding on the least substituted carbon. All right, that's it for this video, and I will see you in the next video.